Mercury has been keeping something beneath its surface for 4.5 billion years. Scientists sent a spacecraft to orbit it for 4 years. What they found didn't match any of their models. Messenger arrived at Mercury in 2011 and spent 4 years in orbit. It mapped the entire planet, sampled its magnetic field, fired lasers at its poles. Everything it found was published, peer-reviewed, and discussed very carefully. Not because the scientists doubted the data, but because the data contradicted the theory they'd been using for decades. The iron core stretches more than 80% of the way to the surface, nearly twice what planetary formation predicted. How did a planet that close to the Sun end up with a core that large? The magnetic field is displaced northward by 20% of the planet's radius, unlike anything in the solar system. What is driving it? And there is water ice, confirmed by 3 independent instruments in 2012, sitting in permanently shadowed craters on a planet where the surface reaches 430 degrees Celsius. Tonight, we go through 6 of these secrets. What they are, what they broke in our models, and what no one has been able to explain yet. By the end of tonight, you'll understand exactly why Mercury is the most misunderstood object in the solar system. If this is the kind of night you return to, subscribe. It helps this quiet universe keep growing. Let's begin. The first secret, the core that cannot be. On the 30th of March 2012, the journal Science published 7 papers simultaneously, all drawing from the same source. The first full year of data from the Messenger spacecraft orbiting Mercury for the first time in history. Sean Solomon, the mission's principal investigator at the Carnegie Institution of Washington, had spent more than a decade designing the mission and guiding it through 6 years of interplanetary transit before it finally settled into orbit in March 2011. The papers described a planet that matched none of the predictions made before it arrived. 3 of the 7 papers addressed Mercury's interior directly. Together, they confirmed what a magnetic field anomaly detected in 1974 had implied but could not prove. Mercury's iron-rich core occupies more than 80% of the planet's radius, and part of it remains liquid today. This was not a revision of existing planetary models. It was a challenge to the theoretical framework used to explain why rocky planets form the way they do. The expectation going in, built on decades of solar nebula modeling, was that a planet at Mercury's distance from the Sun would have a rocky composition broadly similar to Earth's. A silicate mantle comprising roughly 70% of the planet's mass, a metal core making up the remaining 30%. What Messenger confirmed was approximately the reverse. Roughly 70% of Mercury's mass sits in the iron core. The rocky mantle and crust together account for roughly 30%. Of the planet's radius of 2,440 kilometers, more than 2,000 are iron. The rock above it is a shell. The question the 2012 papers could not answer, and the question that still lacks a satisfying resolution, is how a rocky planet forms with this composition. It was not what the models predicted. It was not close. And proximity to the answer has not improved substantially in the years since Messenger's instruments confirmed the dimensions. Proximity to the Sun, it turns out, is not the same as proximity to understanding. Mercury has been demonstrating this since 1974. In 1974, Mariner 10 flew past Mercury 3 times. On each pass, its magnetometer detected a magnetic field. This was immediately puzzling. Mercury is too small, by standard models, to generate an active dynamo. A dynamo requires a large reservoir of electrically conductive liquid in vigorous convection, the mechanism behind Earth's magnetic field. Mercury's interior, by every model available in 1974, should have cooled and solidified billions of years earlier, making a dynamo impossible. Yet the field was real, weak but unambiguous, detected on 3 separate flybys. The planetary science community noted the anomaly, published it, and moved on. Mercury was difficult to reach. Other priorities dominated. 37 years passed. Messenger arrived in 2011, carrying instruments specifically designed to probe what Mariner 10 had hinted at. What it found was not a refinement of the picture. It was a systematic rewriting of it. There is a way to make Mercury's interior geometry tangible, and it requires only a comparison of distances. The straight-line distance from Los Angeles to New York City is roughly 4,300 kilometers. Mercury's radius from center to surface is approximately 2,440 kilometers, a little more than half that distance. Of those 2,440 kilometers, the rocky shell that forms everything visible from orbit, the crust, the mantle, the craters, the cliffs and plains, and ancient lava flows, accounts for roughly 400 kilometers. The iron core extends the remaining 2,040 kilometers from the base of the rocky shell to the planet's center. If you drilled from Mercury's surface to its core, you would pass through rock for a distance shorter than the width of Arizona. Everything below that, 83% of the journey to the center, Earth's iron core occupies roughly 55% of the planet's radius. Mars, approximately 30%. The Moon, roughly 25%. There is no other rocky body in the solar system where the core-to-planet ratio approaches Mercury's. Messenger's surface chemistry instruments added a layer of complication. The surface of Mercury is rich in volatile elements. Sulfur at concentrations 3 to 4 times higher than Earth's crust. Potassium, sodium, chlorine. Materials that evaporate in intense heat. If Mercury formed in the extreme temperatures close to the young proto-sun, as the original models required, these volatiles should have been driven away during formation. Yet they are there, distributed across the entire surface, at concentrations that could not result from later contamination alone. The combination of an anomalously large iron core and an unexpectedly volatile-rich surface is the central contradiction of Mercury's composition. The iron says the planet formed hot. The volatiles say it retained material that cannot survive extreme heat. These two facts, both measured by the same spacecraft, point in opposite directions. A planet is not supposed to be both things at once. The mass distribution that Messenger confirmed makes the contradiction specific. Approximately 70% of Mercury's total mass is in the iron core. The remaining 30% of mass, the silicate mantle and crust, contains the volatile elements at concentrations inconsistent with the high-temperature formation environment that the core's size appears to require. Everything in Mercury's interior and surface chemistry is in tension with everything else. When planetary scientists confront a body that doesn't fit the model, the first question is, what do we change? The second question is harder. Which change is forced by the data? And which is imposed by a theory the field is reluctant to discard? For Mercury's core problem, 3 explanations have survived long enough to be examined seriously. None has been ruled out. None has been confirmed. The first is the giant impact hypothesis. Under this model, Mercury was once a much larger planet, perhaps 2 to 4 times its current mass, with a proportionally more substantial rocky mantle. At some point in the early solar system, before planetary orbits had fully stabilized, a large protoplanetary body collided with early Mercury at high velocity. The impact stripped away most of Mercury's silicate mantle, leaving a remnant dominated by the original planet's iron core. Computer simulations published by Eric Asfaug and Andreas Rufer in 2014 described a variant they called a hit-and-run collision, not a direct impact, but a glancing blow in which the impactor passed through the outer layers and departed with Mercury's mantle material entrained. This scenario requires less precisely tuned initial conditions than earlier giant impact models. The problem is observational. The mantle material that was stripped from Mercury had to go somewhere. It should exist today as a class of iron-poor asteroids or meteorites in the inner solar system. No such material has been identified. The compositional signature of Mercury's presumed lost mantle has not been found in any meteorite family, which means either the material was scattered beyond the observable inner solar system, fell into the sun, or the impact scenario is wrong. The second explanation is solar erosion. The young sun went through a T-Tauri phase of intense radiation and particle output. Mercury's proximity exposed it to ablation far stronger than any other planet experienced. Under this model, the intense solar wind literally removed Mercury's lighter silicate material over millions of years, leaving the denser iron behind. The mechanism works in the right direction. The quantitative problem is substantial. Calculations of how much material a T-Tauri solar wind can remove from a body at Mercury's distance fall well short of what would need to be removed to explain the current core fraction. The mechanism is real, the magnitude is insufficient. The third explanation proposes that Mercury's composition is not about removal, but about formation. In the innermost region of the protosolar nebula, temperatures were high enough that only the most refractory materials, those with high condensation temperatures, could solidify and participate in planetary growth. Iron condenses at higher temperatures than silicates. Mercury may have formed from the available solid material at that distance, which was predominantly iron. No catastrophic stripping required. This hypothesis has the cleanest theoretical foundation. It runs directly into the volatile problem. A planet formed from refractory materials in extreme heat should not have sulfur and potassium at its surface in the concentrations Messenger measured. The most thermodynamically consistent explanation for the core contradicts the most direct surface measurement. All three explanations remain in the literature. The Bepi-Colombo mission, which arrived at Mercury in 2025, has listed determining Mercury's formation mechanism among its primary scientific objectives. Messenger established the dimensions of the problem. The cause remains unresolved. Mercury does not orbit the Sun in a circle. Its orbit is the most elliptical of any planet, ranging from roughly 46 million kilometers at closest approach to nearly 70 million at its farthest. As it traces this path, the Sun's gravitational pull varies, creating a complex torque on the planet. The result is a 3-to-2 spin-orbit resonance. Mercury completes exactly 3 rotations for every 2 orbits around the Sunday. This resonance was not known until 1965, when Gordon Pettengill and Rolf Dice used the Arecibo Observatory's radar to measure Mercury's rotation period directly. The measurement gave 59 days, not 88 as astronomers had assumed for nearly a century of mistaken visual observations. The error had persisted because Mercury always shows the same face toward Earth near its closest approach. Radar was needed to catch what the eye had missed. Jean-Luc Margot, a planetary scientist at UCLA, used this resonance to probe Mercury's interior before any spacecraft arrived. The key measurement is libration, the slight wobble in Mercury's rotation rate as its orbital speed varies with distance from the Sunday. A completely solid planet responds to this gravitational variation as a rigid body. A planet with a liquid outer core responds differently. The liquid decouples partially from the solid mantle, and the libration amplitude takes a different value. By tracking Mercury's rotation with radar from Earth-based telescopes and combining those measurements with careful modeling, Margot's team determined in 2007, published in Science, that Mercury's libration amplitude was 38.5 plus or minus 1.6 arc seconds. This value is consistent only with a liquid outer core. A fully solid Mercury would produce a different number. The liquid outer core was confirmed before Messenger's orbit insertion. Messenger's precision gravity measurements, by tracking tiny Doppler shifts in the spacecraft's radio signals from Earth over 4 years of orbit, confirmed the liquid layer independently and refined its dimensions. After 4.5 billion years, in a planet 1/18th the mass of Earth, that close to the Sunday, standard thermal models predict that Mercury should have fully solidified long ago. Earth's outer core remains liquid because Earth is large enough that radiogenic heating in the mantle, combined with the heat released as the solid inner core grows, keeps the outer core above iron's melting point. Mercury should have exhausted these sources before the Cambrian explosion was a memory on Earth. The most likely reason Mercury's outer core remains liquid is sulfur. A few percent of iron sulfide dissolved in the iron lowers the melting point by tens of degrees. Enough, potentially, to explain why the outer core never fully solidified. Messenger found sulfur concentrations at the surface 3 to 4 times higher than in Earth's crust. Whether the surface sulfur reflects the core's sulfur content cannot be determined from orbit. The two reservoirs are separated by 400 kilometers of rock, but the surface measurement is consistent with the hypothesis and the two anomalies, the anomalously large volatile content and the anomalously persistent liquid core, may have the same cause. The liquid core is not in doubt. Why it's still liquid is, and the magnetic field that liquid core generates turns out to be the most geometrically peculiar dynamo anywhere in the solar system. The giant impact hypothesis requires that Mercury once had a much larger silicate mantle, and that the collision stripped most of it away. If this happened, that material had to go somewhere. It could not simply disappear. The stripped mantle would have been launched into solar orbit as a swarm of rock fragments, some of which should have evolved into a recognizable population of asteroids or contributed to meteorite families that have since fallen to Earth. Geochemists have looked for Mercury's lost mantle in the meteorite record. The search has an identifiable target. Mercury's surface spectra show a mantle-derived rock with low iron oxide content, specific ratios of sulfur and calcium, and a distinctive volatile fingerprint unlike any known meteorite group. If pieces of Mercury's original mantle were scattered through the inner solar system by a giant impact, their geochemical signature would be detectable in recovered samples. No meteorite family has been identified as Mercury mantle fragments. This is negative evidence, the kind that is inherently weaker than a positive detection. But it is evidence nonetheless. After decades of analysis across tens of thousands of recovered meteorites, no candidate population has emerged. The stripping event should have produced material, and the material should be findable, and it has not been found. This does not disprove the giant impact. It constrains it. Eric Asforg and Andreas Rufer's 2014 hit-and-run model proposed that the impactor, rather than being destroyed on contact, passed through Mercury's outer layers and departed carrying the stripped mantle material with it, meaning the debris went into an orbit associated with the impactor, not Mercury. Depending on where that impactor subsequently traveled, its payload of stripped Mercurian mantle could have been scattered into the outer solar system, delivered to Venus's environs, or eventually fallen into the Sun during a later period of orbital instability. Any of these outcomes would explain the absence of Mercury-derived meteorites on Earth. The hit-and-run geometry also relaxes the energy constraints on the collision. A glancing blow requires less precise conditions than a head-on impact and produces a smaller immediate debris field. The impactor continues moving after the collision, carrying most of the stripped material, which has the consequence that Mercury retains its original orbital position while the impactor migrates. Under some simulations, this even explains why Mercury is now in such a low angular momentum orbit, close to the Sun with high eccentricity, because the mass stripping event changed its orbital energy. But these are simulations. They reproduce Mercury-like objects under carefully chosen initial conditions. The initial conditions themselves are not constrained by any independent observation. The hypothesis explains what we see without being testable by what we can currently measure. It is possible, physically coherent, and immune to disproof until either the lost mantle material is found or a seismological measurement of Mercury's interior reveals the compositional signature of a post-impact body. What can be said with confidence is that the composition problem has not been resolved by 40 years of model building following Mariner 10. The 2012 Messenger papers established the dimensions of the problem more precisely. The cause remains, in the strictest scientific sense, unknown. Proximity to understanding is not the same as understanding. Mercury has been maintaining this distinction quietly since 1974. Every hypothesis for Mercury's composition makes specific predictions that go beyond the core fraction alone. Testing those predictions requires data that Mercury carries in its interior, and identifying what specific data would discriminate between hypotheses is itself a scientific result. It tells you what to build, what to measure, and what kind of mission would actually close the question. The giant impact hypothesis predicts a specific interior structure. A Mercury that was once larger, with a full silicate mantle, and then lost most of that mantle to a high-energy collision, would be expected to have a mantle whose composition reflects the residual fraction that was not ejected. A mantle that was processed by the impact event. Impact processing at the energies involved would melt and rehomogenize the silicate material, erasing the compositional layering that forms in a slowly cooling magma ocean. The predicted mantle would be roughly homogeneous in composition from its base to the crust, with a melting and solidification age consistent with the impact event. The high-temperature condensation hypothesis predicts a different structure. If Mercury formed from the most refractory available solids at its orbital distance, those solids would include not just iron but also refractory oxides of calcium, aluminum, and magnesium, the materials found in calcium-aluminum-rich inclusions in primitive meteorites, which are among the oldest solids in the solar system. A Mercury formed by this mechanism would have a mantle rich in these refractory oxides, with a geochemical character distinct from Earth's mantle and from any meteorite family that originated at greater orbital distances. The predicted trace element ratios: calcium to aluminum, aluminum to silicon, would fall in a specific range that no other process produces. A seismometer on Mercury's surface would constrain the mantle density structure and the crustal thickness globally, from which the mantle composition can be bounded, combined with surface geochemistry measurements at the precision that a landed instrument can achieve. Versus the orbital measurements of MESSENGER, the two datasets would overlap enough to discriminate between the two main hypotheses. The inner core radius, if measurable seismically, provides an additional constraint. A giant impact leaves the core with a composition determined by what survived the stripping event, while high-temperature condensation leaves the core with a composition determined by the iron available in the hot nebula region. These differ in their sulfur and light element content, which changes the inner core size at a given age and temperature. The measurement gap is not theoretical ambiguity. It is an instrumental gap. The answer to Mercury's formation question is in the planet. The planet is accessible, closer to the Sun than any other target in the solar system, reachable with less total delta V than Mars from certain launch windows. The barrier is the surface environment: 430 degrees Celsius in daylight, negative 180 at night, a daily cycle of 600 degrees over 59 Earth days. No battery chemistry currently operational survives this thermal cycling without degradation. No conventional electronics survive the temperature extremes without specialized thermal protection that adds mass and complexity to any surface system. The engineering problem is hard, but not theoretically unsolvable. Materials with the required thermal properties exist. Building a spacecraft system that incorporates them into a working science payload has not yet been funded. The question waits. Not in a state of permanent mystery, the boundaries of the unknown are well defined. The instruments needed to resolve it are physically realizable. The planet sits at a distance of between 46 and 70 million kilometers from where you are right now. It is the nearest large rocky body that humanity has visited and not yet fully understood. That this is still true, in the 7th decade of the space age, is not a failure. It is an accurate accounting of how hard planetary science is when the answer requires landing on a surface that no spacecraft has survived. The second secret: the field that defies the rules. Every confirmed active planetary dynamo in the solar system, Earth, Jupiter, Saturn, Uranus, Neptune, is generated by convective motion in a large shell of electrically conductive fluid. The physics is well understood. As fluid moves through the magnetic field it carries, it amplifies that field, sustaining it against the natural tendency toward diffusive decay. The larger the convecting shell and the more vigorous the convection, the stronger the resulting field. Mercury's liquid outer core is thin. The boundary between the solid inner core and the liquid outer core sits somewhere between 400 and 800 kilometers above the planet's center. Estimates vary depending on the assumed density and composition of the two layers. The liquid shell available for convection is at most 1,000 kilometers thick, and possibly much less. Earth's liquid outer core is roughly 2,300 kilometers thick. The convection in Mercury's comparatively thin shell is expected to be sluggish, producing a weak, diffuse magnetic field. That prediction is, in a narrow sense, correct. Mercury's field is roughly 1% of Earth's at the equator, too weak to be detected directly from Earth's surface. But the field is not merely weak, it has a geometric property that no planetary dynamo model predicts from first principles, and which the leading theoretical explanation requires specific internal conditions that cannot currently be verified. Ulrich Christensen, a planetary physicist at the Max Planck Institute for Solar System Research in Göttingen, proposed in 2006 that Mercury's field might be generated not by convection throughout the entire liquid outer core, but by convection in a thin shell at depth, what he called a deep dynamo, operating in an iron snow zone. In parts of Mercury's outer core, iron crystals may precipitate from the liquid as it cools, sinking downward and creating a compositional buoyancy that drives convection in a narrow layer near the core mantle boundary. The dynamo is real and ongoing, but confined to a small region deep inside the planet. The field generated in this deep layer must then travel upward through the overlying, nearly stagnant liquid iron before emerging at the surface. A conductor in motion generates and amplifies magnetic fields. A conductor at rest absorbs and attenuates them. The nearly stationary liquid iron above the deep dynamo acts as a filter, weakening and smoothing the field before it exits the planet. This mechanism would explain why Mercury's external field is weak and smooth. The signatures of an internally generated dynamo that has been filtered rather than simply diminished. And it predicts something else. A field that might be displaced from the planet's center, because the deep convecting layer is not perfectly symmetric inside the outer core. Its effective magnetic center is not the same as the planet's geometric center. The field that emerges at the surface would be offset. Earth's magnetic field is an imperfect dipole. The axis of the magnetic field is tilted roughly 11 degrees from the rotation axis, and the field's effective center is displaced from Earth's geometric center by roughly 450 kilometers, about 7% of Earth's radius. This offset is considered modest. It produces a measurable north-south asymmetry in field strength, but does not fundamentally alter the magnetosphere's structure. Mercury's field is displaced northward from the planet's geometric center by approximately 480 kilometers, about 20% of Mercury's radius. The same physical offset, a different planet, and the geometric fraction is 3 times larger. The magnetic equator, where the field runs parallel to the surface, lies not near Mercury's geographic equator, but in the northern hemisphere. Brian Anderson and his team at the Johns Hopkins University Applied Physics Laboratory, who led the messenger magnetometer analysis, published detailed maps of this structure beginning in 2011. The asymmetry has direct physical consequences. The magnetopause, the boundary where Mercury's magnetic field holds back the solar wind, sits at different altitudes over the northern and southern hemispheres. Over the northern hemisphere, the magnetopause is at roughly 1.5 Mercury radii from the surface. Over the southern hemisphere, it is closer to 1 Mercury radius. The difference means the solar wind regularly penetrates to within a few hundred kilometers of Mercury's southern surface. MESSENGER measured energetic particle impacts on the southern surface at rates far exceeding those in the north. The southern hemisphere of Mercury faces the full intensity of the solar wind with only minimal magnetic protection. The northern hemisphere sits behind a partial shield No other planetary dynamo in the solar system exhibits this degree of north-south asymmetry relative to the planet's size. Saturn's field is the most symmetric of any known planetary dynamo, so precisely centered that its offset has not been measurably resolved above zero. Earth's offset is real but modest. Mercury's is dominant. The southward hemisphere of the planet closest to the Sun is also the most exposed to the Sun's particle output. These are not independent facts. The Christensen Deep Dynamo model predicts a northward offset, but does not predict the specific 20% value from first principles. The model's prediction depends on conditions inside Mercury's core that cannot be measured from orbit. The solar wind is not just a hazard to spacecraft electronics. At Mercury's southern hemisphere, where the magnetopause barely holds, it is an active geological force. When the solar wind's magnetic field threads through Mercury's weak magnetosphere and connects directly to the surface, a process called magnetic reconnection, energetic solar particles travel along those connected field lines directly to the ground. The footprints of these connections migrate across the southern hemisphere as Mercury orbits and as the solar wind direction fluctuates. At these footprint locations, solar particles strike the surface with enough energy to knock individual atoms free from the rock, a process called sputtering. Sodium, potassium, calcium, and magnesium atoms, liberated by sputtering, drift upward into Mercury's exosphere, the planet's trace atmosphere, too thin to trap heat or transmit sound, an ensemble of individual atoms temporarily floating above the surface before falling back or escaping to space. Messengers, Mercury atmospheric and surface composition. Spectrometer measured this exosphere in detail across multiple orbits and seasons. The exosphere varies with Mercury's orbital position. Near perihelion, when Mercury is closest to the Sun and the solar wind is most intense, the exosphere density increases. The sodium tail, a stream of exospheric sodium atoms pushed anti-sunward by radiation pressure, extends for millions of kilometers behind the planet, visible to Earth-based sodium filter telescopes. What the exosphere measurements reveal about the surface is useful precisely because it samples regions that no camera or spectrometer on MESSENGER ever directly imaged. The atoms floating above the surface carry chemical information about the rocks below them. The exosphere measurements, independently of the surface chemistry measurements, confirmed elevated sodium, potassium, and sulfur-bearing species above Mercury, consistent with, and in some cases sharper than, the direct surface spectrometry. Mercury has been exhaling its own surface into space for 4 billion years. The atoms lost by sputtering are not replenished by any known geological process. Over billions of years, the accumulated loss is real. If small, Mercury is, in this sense, a planet that the solar wind is slowly taking apart, one atom at a time, primarily from its southern hemisphere, because the magnetic field that protects the north does not extend far enough south to protect the rest. The Deep Dynamo model proposed by Christensen in 2006 remains the leading framework for explaining Mercury's magnetic field. It correctly predicts the field should be weak, smooth, and offset northward. It does not predict the specific 20% displacement. The gap between what the model requires and what can be confirmed is located precisely inside the planet, in the conditions of the outer core that no instrument has directly sampled. A competing idea proposes that the offset arises not from the dynamo's geometry but from Mercury's internal structure. If the solid inner core is itself displaced northward from the planet's geometric center, it would asymmetrically heat the overlying liquid, driving more vigorous convection in the northern part of the outer core and producing a magnetic field whose effective center is shifted north. An off-center inner core would produce an off-center field. This idea is geometrically consistent with the observations. It is also unverifiable with current instrumentation. Determining whether Mercury's inner core is centered requires measuring the planet's seismic structure. Tracking the speed and reflection patterns of seismic waves from Mercury quakes through the deep interior. No seismometer has ever been placed on Mercury. The question is structurally identical to asking whether Earth's inner core is displaced from center before seismology existed. The answer is in the interior, and the interior has not been directly accessed. Bepi Colombo's 2 spacecraft configuration will provide 3-dimensional mapping of Mercury's magnetic field. The magnetospheric orbiter flying higher orbits while the planetary orbiter flies lower, giving simultaneous measurements at 2 altitudes. This will refine the field model significantly, narrowing the parameter space the deep dynamo must occupy. But the deep interior itself, the iron snow zone, the liquid shell geometry, the position of the inner core boundary, will remain unreachable until a seismometer reaches the surface. Mercury has an atmosphere in the technical sense. There is material above its surface at higher than vacuum density, but it is an atmosphere in the way that a single thread is a blanket. The total atmospheric pressure at Mercury's surface is approximately 5 times 10 to the negative 15th bar, roughly 100 trillion times less than Earth's sea level pressure. Individual atoms travel from surface to space and back without colliding with each other. Atmospheric scientists call this an exosphere, a surface boundary exosphere. In Mercury's case, meaning the material immediately above the surface is the atmosphere, without a distinct lower boundary where conditions change from solid to gas to sky. Messenger's Mercury Atmospheric and Surface Composition Spectrometer, or MACS, spent 4 years measuring this exosphere systematically. It detected sodium, potassium, calcium, magnesium, and aluminum in the gas above Mercury's surface. Each element appears at different altitudes, with different spatial distributions, and varies in density with Mercury's orbital position and with local time of day on the planet's surface. The patterns encode information about where each element comes from and how efficiently it escapes from the surface. Sodium is the most abundant detected species and the best studied. Ground-based sodium filter telescopes, which can observe Mercury's sodium exosphere from Earth by imaging the specific wavelength of sodium's spectral emission, have been watching Mercury's sodium cloud for years. Messenger mapped the 3-dimensional distribution of sodium around the planet. The sodium is concentrated in 2 bright patches over Mercury's poles, the cusp regions where magnetic reconnection events funnel energetic particles to the surface and drive sodium off the rocks most efficiently. The sodium density peaks near perihelion, when solar radiation pressure and solar wind intensity are highest, and decreases near aphelion. During perihelion passes, the sodium forms an extended tail stretching millions of kilometers behind Mercury, anti-sunward, pushed by radiation pressure from the sunday. Calcium and magnesium, detected by MACS at higher altitudes than sodium, have spatial distributions that differ from sodium's in ways that are not yet fully explained. Calcium is concentrated at Mercury's dawn terminator, the line on the planet where darkness transitions to daylight, at levels higher than thermal models of exospheric transport predict. This calcium enhancement at dawn has been attributed to impact vaporization by interplanetary dust concentrated in Mercury's orbital plane, or to some chemical release mechanism that operates at the specific temperatures found at the transition from night to day on Mercury's slowly rotating surface. Neither explanation is fully satisfying. The exosphere is not just a curiosity of Mercury's extreme environment. It is a sampling instrument. Every species detected above the surface came from the surface material below the detection point. By mapping the exosphere's spatial distribution over 4 years of orbital observations, the MACS team accumulated a global compositional map of Mercury's surface that extends the direct spectrometry measurements to regions of poor lighting and high latitudes where surface reflectance measurements are difficult. The exosphere profile is a chemical shadow of the terrain below. What the exosphere measurements confirmed, and in some places sharpened, is the volatile-rich surface composition that the direct spectrometry found. The sodium and potassium densities above specific geological units are higher above regions rich in low reflectance material, suggesting that the volatile content of the LRM-bearing terrain is genuinely elevated relative to the average surface. The exosphere and the hollows and the surface chemistry are consistent parts of a single picture. A planet whose shallow interior is chemically more complex than its formation environment should have permitted, losing that complexity slowly to space, one atom at a time. The third secret is at the opposite end of the planet from the unprotected southern hemisphere, and it involves the one thing that nothing about Mercury's position would lead you to expect. The solar wind does not simply push against Mercury's magnetosphere in a uniform, steady way. It pokes through it when the interplanetary magnetic field carried outward from the Sun has a southward component, which it frequently does as the field rotates and fluctuates. It can reconnect with Mercury's northward-pointing magnetic field at the dayside magnetopause. The two opposing field lines break and reconnect, creating a temporary bundle of merged field lines that threads from the solar wind directly into Mercury's magnetosphere. The bundle rotates, twisted by the geometry of reconnection, and the resulting structure has been described as a magnetic tornado, a vortex of field lines funneling solar plasma directly onto the planet's surface at the reconnection footprint. Brian Anderson and his colleagues on the Messenger magnetometer team detected these flux transfer events systematically in orbital data published beginning in 2011. At Earth, similar events occur but are relatively rare and short-lived. Earth's large, strong magnetosphere limits the rate and duration of reconnection. Mercury's weak magnetosphere offers far less resistance. The events at Mercury are more frequent, occurring roughly once every 8 minutes, compared to once every few hours at Earth, and the plasma delivered through each event reaches the surface with minimal dissipation. The footprints of these reconnection events on Mercury's surface are not fixed. They migrate with Mercury's orbital position, with the orientation of the interplanetary magnetic field, and with the intensity of the solar wind. At perihelion, when Mercury is closest to the Sun and the solar wind pressure is highest, the reconnection rate increases, and the particle flux reaching the surface through flux transfer events intensifies. At aphelion, the rate decreases, the particles delivered to the surface through these events, primarily electrons and protons at energies of hundreds to thousands of electron volts, are energetic enough to drive chemical changes in surface minerals. They can break molecular bonds in volatile-bearing compounds, liberating volatile species that then enter the exosphere. This creates a spatially and temporally variable energy source at the surface, not the steady solar heating that bakes the sunlit terrain at 430 degrees, but periodic intense particle bombardment at the reconnection footprints, following an orbital rhythm tied to Mercury's position around the Sunday. Several researchers have noted that this orbital modulation of surface bombardment could contribute to hollow formation. The sublimation rate of volatile minerals depends on temperature and on the energy available to break surface bonds. A site exposed to episodic high-energy particle bombardment during perihelion passes, when the planet is at its closest to the Sun and the solar wind is strongest, would experience more volatile loss per orbit than a site receiving only thermal energy. If hollows form where volatile-bearing rock is exposed, and if the formation rate correlates with the energy available to drive sublimation, the periodic particle bombardment from magnetic reconnection may be one of the missing energy inputs that explains why hollow formation is still ongoing. This connection has not been confirmed. It is a proposed mechanism, supported by physical reasoning and consistent with the orbital patterns in the exosphere data, but not yet tested against a quantitative model of hollow growth rates. It illustrates the degree to which Mercury's anomalies are entangled, the magnetic field asymmetry, the volatile rich composition, and the active surface geology may be aspects of the same coupled system rather than separate problems with separate causes. Mercury is a small planet. Planetary scientists initially expected that its small size would make it simple. What Messenger showed is that its small size means that several processes operating at different scales, the deep dynamo, the magnetospheric interaction, the surface chemistry, the geological activity, are all close enough together that they interact. The interior influences the surface. The surface influences the exosphere. The exosphere records the interior. In a larger planet, these systems are separated by distance. In Mercury, they are in contact. Christensen's deep dynamo model names a specific physical process: iron snow, as the engine that keeps Mercury's dynamo running despite the thin liquid shell and weak convective driving. Understanding what iron snow is makes the model either more or less plausible, depending on your intuition about condensation in metal liquids under extreme conditions. The physics is ordinary. The setting is not. In any liquid metal, the conditions under which the metal begins to solidify depend on temperature and pressure. At higher pressures, solids generally require higher temperatures to melt. The phase boundary shifts. Inside Mercury's outer core, the pressure varies with depth. Greater at the bottom of the liquid shell, near the boundary with the solid inner core, and lower at the top of the liquid shell, near the boundary with the rocky mantle. The temperature also varies with depth, following a gradient that reflects how quickly Mercury's interior is losing heat. If the temperature gradient drops faster than the melting point gradient as you move from deeper to shallower regions of the outer core, there is a zone near the top of the outer core where the liquid iron is cold enough to begin solidifying. In this zone, the iron snow zone, small crystals of nearly pure iron precipitate out of the liquid. Here is where the analogy to snow becomes precise. The crystals form at relatively high altitude in the outer core, where it is coldest, and are initially suspended in the liquid. As they grow, their density exceeds that of the surrounding liquid. In a pure iron ocean, they would simply sink. But Mercury's outer core is not pure iron. It contains significant quantities of lighter elements, almost certainly including sulfur. The liquid iron with sulfur dissolved in it is somewhat less dense than the solid iron crystals that precipitate from it. The crystals are denser than the liquid. They sink. As the crystals fall through the outer core, they encounter warmer regions where the temperature is too high for them to remain solid. They melt. The iron they contribute to the lower liquid enriches it slightly in iron. The liquid they left behind at the top of the outer core is now enriched in sulfur, the sulfur that was displaced from the regions where iron crystallized. This sulfur-enriched liquid is lighter than the iron-rich liquid below it. It rises. This rising sulfur-enriched, light liquid is the convective motion that drives the dynamo. Not thermal convection, the simple rise of hot fluid and fall of cold fluid, but compositional convection, the rise of chemically distinct, less dense fluid driven by the ongoing precipitation of iron crystals in the upper part of the outer core. As long as Mercury's outer core continues to cool, and as long as the iron snow zone persists, this compositional convection continues. The dynamo runs. The elegance of the mechanism is that it produces a weak, persistent dynamo from conditions that would otherwise seem insufficient. Pure thermal convection in Mercury's thin liquid shell might be too weak to sustain a self-amplifying magnetic field. Compositional convection driven by iron snow provides the extra buoyancy that thermal convection alone cannot. And because the iron snow process is governed by the slow, steady cooling of the interior rather than by rapid convective overturning, it produces a field that is smooth and stable over geological timescales, consistent with what Mercury's surface record implies about a long-lived, relatively steady magnetic field. The question that Christensen's model cannot answer with current data is where exactly the iron snow zone sits, how thick it is, and whether the compositional convection it drives is sufficient to explain the observed field geometry, including the 20% northward offset. These depend on the specific composition of the outer core, the sulfur content, the concentration of any other light elements, which Messenger could not measure and which Bepi-Colombo cannot measure directly. The iron snow mechanism is consistent with what is known. Whether it is the correct mechanism requires access to the interior that no instrument has yet achieved. The third secret, the ice in the fire. In 1991 and 1992, Two research groups used Earth-based radar observatories to study Mercury's surface. Jack Harmon at the National Astronomy and Ionosphere Center and Martin Slade at the Jet Propulsion Laboratory used the Goldstone Solar System radar in California to bounce microwave signals off Mercury and measure the reflections. The technique, called dual circular polarization, is sensitive to the structure and electrical properties of surface materials. Water ice, because it is highly transparent to radar and capable of internal scattering, produces a distinctive signature. A high ratio of same-sense to opposite-sense reflected power, called a high circular polarization ratio, that bare rock does not produce. When Harmon and Slade processed their data, they found several anomalously bright regions on Mercury's surface. Published in Science in 1992, the paper was careful. The authors identified ice as one possible explanation for the radar brightness, but noted that other materials, certain sulfur compounds, highly reflective silicates, could in principle produce similar signatures. Mercury's polar geometry made ice a credible candidate. Mercury's axial tilt is 0.034 degrees, effectively zero compared to Earth's 23.4 degrees. At this tilt, the poles receive sunlight at extreme grazing angles year-round. Impact craters at high latitudes have floors that permanently face away from the sun. The same crater floors that last received direct sunlight. In some cases, before the late heavy bombardment reshaped the inner solar system, thermal models predicted that the permanently shadowed regions inside those polar craters could be as cold as negative 170 degrees Celsius, colder than anything in Earth's natural environment. Despite sitting on the planet closest to the Sunday, at negative 170 degrees, water ice is thermodynamically stable. In a vacuum, without any sublimation driving heat flux, ice deposited billions of years ago would remain. The radar signature was suggestive. The thermal argument was consistent. The question was whether the two together constituted confirmation. They did not. The uncertainty persisted for 20 years. In November 2012, 5 papers published simultaneously in Science ended the 20-year uncertainty. Messenger had spent its first year and a half in orbit, mapping Mercury's poles with 3 independent instruments, whose physical measurement principles have nothing in common with each other. The fact that all 3 converged on the same conclusion. Water ice, concentrated in the same permanently shadowed craters that the 1,992 radar had flagged, made the result as well confirmed as any direct measurement could be from orbit. The first instrument was the neutron spectrometer. David Lawrence, a nuclear physicist at the Johns Hopkins University Applied Physics Laboratory who led the analysis, used a technique borrowed from asteroid and moon exploration. When cosmic rays strike a planetary surface, they generate neutrons. The energy distribution of those escaping neutrons is sensitive to the hydrogen content of the surface material. Hydrogen nuclei are particularly efficient at thermalizing neutrons, slowing them, in a way that hydrogen-poor rock is not. Lawrence's team detected a hydrogen enhancement at Mercury's North Pole, spatially correlated with the radar bright regions identified in 1992. The magnitude of the enhancement was consistent with water ice at or near the surface, beneath a thin covering of darker material. The second instrument was the Mercury Laser Altimeter. Designed to measure surface topography by timing laser pulse returns, the altimeter also records the reflectance of surfaces at 1064 nanometers. Ice, in this wavelength range, is highly reflective. Rock is not. When the altimeter beam crossed permanently shadowed regions in Mercury's northern craters, the reflectance values jumped to values inconsistent with any known silicate material. The spatial distribution of the high reflectance regions matched the hydrogen-enhanced regions from the neutron spectrometer and the radar bright regions from 1992. The third instrument was the Mercury Dual Imaging System's wide-angle camera. By using long exposure times to capture faint reflected illumination from crater walls and the surrounding terrain, Messenger's imaging team obtained photographs of permanently shadowed crater floors. The images showed bright deposits in the floors of the deepest, most shadowed craters. Darker deposits appeared in regions of partial shadow at intermediate temperatures. 3 independent physical measurements, 3 different instruments operating on different principles, all pointed to the same locations, and all were consistent with water ice. The 5 papers in Science named specific craters. Prokofiev, at 112 kilometers across, contained the largest confirmed North Polar deposit. Kandinsky, Tolkien, Fuller, and others held smaller but clearly confirmed deposits. The same 3 instruments that confirmed the polar ice also revealed, in combination, that the ice in many locations sits beneath a thin layer of darker material, roughly 10 centimeters thick. The neutron spectrometer found hydrogen consistent with buried rather than surface ice. The laser altimeter measured reflectance lower than clean ice in some regions, intermediate between pure ice and bare rock. The imaging showed these mixed regions as intermediate in brightness, with the darkest deposits at the edges of the shadowed zones and the brightest deposits in the coldest central floors. The dark covering material has a carbon-rich composition based on its spectral behavior and on comparisons with dark material found in Mercury's low-reflectance terrain elsewhere on the planet. Carbonaceous compounds, organic molecules darkened and processed by long exposure to radiation and solar wind bombardment, match the observed spectral signature. These are the kinds of materials commonly associated with cometary nuclei and carbonaceous chondrite meteorites. The implication is that Mercury's polar ice was delivered by comets and carbonaceous asteroids over geological time, and that the same impacts brought organic material along with the water. The organics, being more chemically complex and less volatile than ice, accumulated at the surface of the ice deposits, forming a thin, insulating cap. A 10-centimeter layer of carbon-rich material reduces the sublimation rate of ice beneath it substantially because it absorbs radiation that would otherwise drive water molecules off the ice surface. The dark layer is the reason the ice has survived. It is a thermal blanket, placed there by the same delivery mechanism that brought the water in the first place. Lawrence and colleagues estimated in follow-up work that the deposits could be up to 20 meters thick in the shallowest, most exposed regions, and potentially hundreds of meters thick in the deepest central sections of the largest craters. Prokofiev, in particular. If those depth estimates are accurate, the polar craters of Mercury contain a larger volume of preserved water ice than is currently exposed on the entire surface of Mars. These deposits may have been accumulating for hundreds of millions to billions of years. The oldest may predate the Cambrian explosion on Earth. Stand at the rim of Prokofiev crater at Mercury's North Pole. Behind you, the surface stretches southward in the direction of the Sunday, and toward it, the terrain is catastrophic. Temperatures on the sunlit side of Mercury reach 430 degrees Celsius at local noon. The rocks absorb heat with no atmosphere to distribute it, no wind to carry it, no ocean to moderate it. The surface near the equator, in the hours around noon, is hot enough to melt lead. Nothing organic survives there, and nothing volatile remains for long. In the rocks near your feet, south-facing slopes bake continuously in each long Mercury day of 59 Earth rotations. But at your feet, at the crater rim, the floor below you has not seen the sun since the impact that created it. Perhaps 3 billion years ago, perhaps earlier. The geometry of Mercury's nearly zero axial tilt means the sunlight skims across the rim at a shallow angle, never penetrating. Down on the crater floor, in permanent shadow, the temperature holds near negative 170 degrees. The rocks down there have not moved thermally in geological ages. The water ice below the dark organic cap sits quiet and ancient and patient, unchanged. The solar wind that strips the southern hemisphere does not reach here. The magnetic field converges over the North Pole, creating an additional layer of protection for the polar craters. The organics on the ice surface have been darkening slowly, accumulating damage from occasional cosmic ray bombardment, but the ice underneath them is stable. The water molecules locked in that ice have been in the same positions, in the same crystal lattice, for longer than complex life has existed on Earth. Proximity to the Sun is not the same as warmth. Mercury's polar craters are evidence of this at a scale that feels impossible until the thermometer says otherwise. The same comets that delivered this water to Mercury may have delivered water to early Earth. They may have seeded Mercury's polar craters and Earth's oceans as part of the same episode of late heavy bombardment in the same few 100 million years from the same population of water-bearing objects. If so, the oldest reservoir of cometary water in the inner solar system may not be in the asteroid belt or on a comet nucleus in the outer system. It may be in a permanently shadowed crater on the planet closest to the Sunday, quiet, dark, and chemically unchanged since before animals existed on Earth. The cometary delivery hypothesis is the most widely accepted origin for Mercury's polar ice, but it is not the only one, and the distinction matters for what the ice tells us about the early inner solar system. Comets are mixtures of water ice, dust, and organic molecules. The dark organic cap found on Mercury's ice deposits is compositionally consistent with material delivered by comets, and the isotopic ratios of hydrogen in cometary water have been measured for several known comets. If Mercury's polar ice came from comets, its hydrogen isotope ratio, specifically the ratio of deuterium to ordinary hydrogen, should resemble that of the cometary sources. Messenger did not have the instrumental capability to measure this ratio directly. Bepi-Colombo's neutron spectrometer has improved sensitivity, but measuring isotope ratios from orbit remains challenging. A landed instrument with a mass spectrometer would resolve the question definitively. Carbonaceous asteroids are the other candidate. They contain water in hydrated minerals, not free water ice, but water bound into the mineral structure. And they also contain organic compounds, in proportions broadly similar to those found in comets. When carbonaceous asteroids impact Mercury, the energy of the impact converts some of the hydrated mineral water into free water vapor, which can then migrate toward the poles and be cold-trapped in the permanently shadowed craters. The organic material from the asteroid would accompany the water, producing a dark cap consistent with what Messenger observed. The delivery rate matters as much as the source. Mercury's polar craters have been accumulating ice since they formed. If the late, heavy bombardment, the period from roughly 4 billion to 3.8 billion years ago, when the inner solar system was struck by an elevated flux of impactors, was the primary delivery event, most of the ice arrived in a geologically brief window and has been sitting in the craters for nearly 4 billion years. If delivery is ongoing, with comets and asteroids still contributing water at a lower rate, the ice may be younger in its uppermost layers, with older ice beneath. The depth profile of the deposits, which Bepi-Colombo's radar instrument may be able to partially constrain, would distinguish between these scenarios. The connection to Earth's water is not incidental. The same questions that researchers ask about Mercury's polar ice. Where did the water come from? When did it arrive? What was the delivery mechanism? Are versions of the same question asked about Earth's oceans? Earth is too large for ice to survive in permanently shadowed craters in the same way. The planet's geological activity mixes and processes water throughout the crust and mantle. But the cometary and asteroidal flux that delivered water to Mercury in the late heavy bombardment was planetary in scope. It hit every object in the inner solar system roughly in proportion to their cross-sectional area. Mercury's polar craters are, in this sense, a cold trap for the same delivery event that contributed to Earth's oceans, an unprocessed residue preserved, because Mercury's geology is too inactive and its poles too cold to recycle it. Reading the chemistry of Mercury's polar ice is, in part, reading the chemical record of early solar system volatile delivery. The ice closest to the top of the deposits may carry information about the most recent delivery events. The ice at the bottom, if any of it has been preserved undisturbed since the late heavy bombardment, would carry information about the delivery environment 4 billion years ago. No mission has yet reached that bottom layer. Bepi Colombo cannot. It will take a drill and a mass spectrometer and a power system that can survive a Mercury winter. The fourth secret is not found at the poles, it is found everywhere else on Mercury's surface, in features so structurally unusual that when Messenger first imaged them, the scientists had no existing category to put them in. The 5 papers published in Science in November 2012 described Mercury's North Polar ice deposits in detail. The South Polar deposits received less attention, not because the evidence was absent, but because Messenger's geometry made the South harder to study. Messenger's orbit was highly elliptical, with its lowest altitude over the northern hemisphere. For most of the mission, the spacecraft passed closest to Mercury's surface in the north, giving the northern terrain the highest resolution coverage. The South Pole was observed at greater distances, with correspondingly lower spatial resolution and a weaker signal-to-noise ratio for the instruments most sensitive to ice. Ground-based radar observations had shown bright, high circular polarization ratio signatures at Mercury's South Pole as well as the North. The same radar signature that flagged the North Polar deposits in the 1992 Harmon and Slade survey. The southern signatures were present, less extensive in coverage, and attributed to the same permanently shadowed crater geometry. Mercury's axial tilt is so close to zero that the geometry producing permanent shadow at the North Pole produces it equally at the South. What the South Pole adds to the picture, beyond being a second instance of the same phenomenon, is a test case for the role of Mercury's asymmetric magnetic field in ice preservation. The Northern Hemisphere sits behind a relatively effective magnetic shield. The Southern Hemisphere is directly exposed to the solar wind for large fractions of each orbit, as the magnetopause in the south descends close to the surface. In principle, the higher particle bombardment in the southern hemisphere could affect the ice deposits, accelerating sputtering of the dark organic caps, altering the sublimation equilibrium, or modifying the chemistry of the ice surface at rates that differ from the north. Whether the southern deposits show evidence of greater radiation damage to their organic caps, then the northern deposits would tell scientists something about whether the magnetic asymmetry has been stable over geological time. A stable asymmetry, the same northward offset, the same differential protection, persisting for billions of years, would produce a measurable difference in the cap chemistry between north and south. A variable asymmetry, the field offset migrating over time, as some dynamo models allow, would produce a more complex pattern. Bepi Colombo's orbital configuration gives it significantly better coverage of Mercury's southern hemisphere than Messenger achieved. The planetary orbiter's orbital parameters will allow regular, low-altitude passes over the South Pole, and its improved spectrometry will provide a direct comparison of north and south polar deposit chemistry. If the organic caps are chemically distinct between hemispheres, more irradiated in the south, it constrains how long the magnetic asymmetry has persisted. If they are similar, either the asymmetry is variable or the radiation effects are too small to detect. The polar deposits are not just water ice in a cold place. They are a record written by the intersection of Mercury's magnetic field, its orbital dynamics, and the cometary history of the inner solar system. The South Pole is a page of that record that Messenger could not fully read. The fourth secret, the hollows. In the summer of 2011, David Blewett, a planetary scientist at the Johns Hopkins University Applied Physics Laboratory, was reviewing Messenger images of Mercury's surface when he found something in the floor of a large impact crater that had no name and no precedent. The features were shallow, irregular depressions, not craters, which are roughly circular and formed by impact, but something different. They were clustered together in groups inside crater floors and on the walls of impact basins. They ranged from tens of meters to roughly 2 kilometers across. Their walls were steep, their floors were nearly flat, and they were extremely bright. Brighter than almost any other material Messenger's cameras had recorded on Mercury. Blewett had spent years studying planetary surfaces. The features had no analogue he could find. They didn't match anything documented on the Moon, on Mars, on any of the asteroids. He brought in collaborators from multiple institutions and spent months testing whether known geological mechanisms could explain the features. Volcanic venting, tectonic extension, impact melt, ice sublimation. None of the existing frameworks fit. The paper he published in Science in September 2011, with 24 co-authors, coined the term hollows for the features. The abstract described them as a new landform of uncertain origin. In the language of planetary geology, this phrase means, "We cannot explain what made these." Nothing in any mission prediction had anticipated them. The Messenger science team had been prepared to find volcanic features, impact craters, tectonic scarps, and chemical anomalies. The hollows were not on any of those lists. They appeared in the images as if the planet had been keeping them specifically for the moment a camera was finally close enough to see. Messenger's cameras returned more than 270,000 images of Mercury across 4 years. Hollows appear in many of them. Once you know the shape, individual hollows are typically between 10 meters and a few kilometers in their longest dimension, though the largest clusters span tens of kilometers. In plan view, looking straight down, they appear as irregular polygons, rounded but not circular, often elongated along some structural feature of the surrounding terrain. Their depth, measured by the Mercury laser altimeter, ranges from a few meters to tens of meters. Their walls are steep relative to their depth. Their floors are nearly flat. The reflectance of hollow floors and walls is up to 3 times the average reflectance of Mercury's surrounding surface. On most rocky bodies in the solar system, extreme brightness means fresh material, rock that has not yet been darkened by prolonged exposure to space weathering, through radiation bombardment and micrometeorite impacts. Space weathering darkens surfaces over time. Bright surfaces are surfaces that have not had enough time to darken. No impact craters have been found on top of hollows. In planetary geology, the presence of superimposed craters constrains the age of a surface. Older surfaces accumulate more craters. The absence of craters on hollow surfaces sets an upper age limit. The hollows are younger than the craters in which they form, and they are possibly much younger. Some estimates place hollow formation within the last 100 million to 1 billion years. Others suggest the process may be ongoing today. Hollows are found at all latitudes and in diverse geological settings. Crater floors, central peak rings inside large impact basins, crater walls, and the outer flanks of ejecta blankets. In Crater Curtis, a 60-kilometer impact basin in Mercury's northern plains, hollow clusters cover most of the crater floor in an irregular mosaic of bright, shallow depressions. In the much larger Rachmaninoff Basin, hollows appear on the peak ring, where the rebound uplift from the impact has exposed deep material. The consistent factor is not location, but rock type. Hollows appear wherever a particular kind of subsurface material has been excavated and exposed. The leading explanation for Mercury's hollows involves sublimation, the direct transition of a solid to a gas without passing through a liquid intermediate phase. On Earth, sublimation is familiar from dry ice. On Mercury, where atmospheric pressure is effectively zero and the sunlit surface reaches 430 degrees Celsius, any material with a high enough vapor pressure at Mercury's temperatures would sublimate continuously when exposed to the surface environment. The hypothesis proposes that the rock beneath Mercury's surface is rich in volatile compounds. Most likely, chlorides, sulfides, or other materials containing volatile-bearing minerals that are stable at depth, shielded from direct solar heating, but sublimate rapidly when excavated by impact and exposed at the surface. When an impact brings this volatile-rich layer to the surface, the exposed material begins sublimating into the vacuum. As it does, the surface retreats, deepening the depression. As the depression deepens, more volatile material is exposed at the walls, and the hollow grows laterally. The bright material surrounding and lining the hollows is the lag deposit, the non-volatile residue left behind after the volatile fraction has departed into space. This mechanism is physically coherent and consistent with Mercury's surface environment. It would explain the brightness. Freshly formed lag deposits have not had time to darken. It would explain the distribution. Hollows appear wherever impacts have excavated to the volatile bearing layer. It would explain the absence of superimposed craters. If the surface is actively receding, new craters cannot accumulate faster than hollows form. The hypothesis has two problems that remain unresolved. The first is compositional. The specific volatile compound responsible for hollow formation has not been identified. Messenger's spectrometers measured the spectral properties of hollow-bearing terrains, but did not have the spatial resolution to directly characterize hollow floor material. The spectral signature is consistent with several possible volatile-bearing minerals, chlorides, graphite, sodium sulfide, but does not uniquely identify any single candidate. The second problem is timing. Mercury has been in its current orbital configuration for billions of years. Impacts have been delivering material to the surface throughout that time. If the volatile-bearing layer can be excavated and sublimates whenever exposed, most of it should have been depleted long ago. Yet the hollows appear fresh, actively forming, not relict features of a past process. Either Mercury has far more volatile material in its shallow subsurface than any current model accommodates, or something is driving the sublimation at rates that only recently accelerated. Perhaps the variation in solar wind flux as Mercury's orbital position changes. Perhaps the tidal heating from the Sun's varying gravitational pull as Mercury moves through its highly elliptical orbit. The hollows are, in a sense, the visible expression of a pattern that runs through all of Mercury's anomalies. Every model of Mercury's formation predicted a volatile poor planet. The models required it. Formation close to the Sun means formation in intense heat, and intense heat means volatiles cannot survive the formation process. Yet Messenger found sulfur at 3 to 4 times Earth's crustal concentration. It found potassium, an element that evaporates at temperatures far lower than the inner solar nebula should have reached at Mercury's position, at concentrations comparable to Earth's. It found chlorine, sodium, carbon-bearing compounds. And now it found hollows, a geological feature that appears to form from the loss of volatile material from Mercury's own subsurface, under conditions that have prevailed for billions of years without apparent depletion. Proximity to the Sun is not the same as composition. Mercury has been demonstrating this since the first surface chemistry spectra arrived. In a 2016 review, Blewett described the hollows as the only geological feature known in the solar system that forms actively through the loss of solid material directly to space via sublimation. Not erosion by wind or water, not volcanic degassing, not tectonic stretching, but the direct conversion of a volatile mineral to gas under the ambient conditions of a planetary surface. They are unique. They are unexplained at the level of their specific chemistry. And they are forming right now. The connection between hollows and the rest of Mercury's anomalies runs deeper than the volatile problem alone. The same solar wind that processes the southern hemisphere, knocking atoms off the surface, feeding the exosphere, may be one of the energy inputs driving hollow sublimation. The magnetic reconnection events that periodically deposit energetic plasma onto specific regions of the surface create local heating that could accelerate volatile loss wherever the hollow-bearing rock type is exposed. The fragmented magnetic protection, the volatile-rich composition, and the active surface geology may be connected into one system. A planet whose interior, surface, and space environment are more tightly coupled than any simple model of Mercury as a small, dead rock had suggested. The question nobody has answered yet is, How fast? Estimating the growth rate of a geological feature requires either direct observation over time, watching the feature change between observations, or a physical model with enough precision to calculate the rate from known material properties. For Mercury's hollows, both approaches face serious obstacles. Direct observation requires two high-resolution images of the same hollow, taken years or decades apart, with enough resolution to detect the size change and enough positional accuracy to confirm the detection is real and not an imaging artifact. Messenger's 4-year mission was too short for this. Any hollow growth detectable over 4 years would imply an extraordinary rate by geological standards, and no such growth was detected. The hollows observed in early Messenger images and re-imaged later in the mission showed no detectable change at the spatial resolution available. This sets an upper bound on the growth rate, but the upper bound is not very tight, because the spatial resolution of orbital imaging limits detection of small changes. Physical modeling of the sublimation rate requires knowing the specific volatile compound responsible, its vapor pressure at Mercury's surface temperatures, and the rate at which solar radiation and particle bombardment supply energy to the sublimating surface. Without knowing the specific compound, the vapor pressure cannot be calculated. Without the vapor pressure, the sublimation rate cannot be determined from first principles. What the models can do is work backward from the hollow population. If the total volume of hollow depressions on Mercury's surface is estimated, and if an assumption is made about how long hollows have been forming, the age of the craters in which they appear sets a maximum age. Then the average growth rate can be bounded. These calculations suggest that the current volatile inventory in the shallow subsurface, if it is being depleted at the rates implied by the hollow volumes, should last for at least hundreds of millions of years under current conditions. The process is slow by human timescales. It is fast by geological ones. The implication is that Mercury will continue to lose its volatile subsurface layer indefinitely as long as the solar heating and particle bombardment continue, and as long as volatile-bearing rock continues to be excavated and exposed, the hollows will spread. The bright depressions will multiply and enlarge. The planet will become incrementally less volatile rich over geological time. How much volatile material remains in the shallow subsurface? The total reservoir available for this ongoing loss is not known. The distribution of hollows is not uniform. It follows the distribution of the low-reflectance graphite-rich material, which in turn reflects the distribution of the primitive crustal layer buried under varying thicknesses of subsequent volcanic and impact deposits. In some regions, the volatile-bearing material may be deeply buried and unlikely to be excavated by the impacts that form the craters in which hollows appear. In others, it may be at the surface, continuously exposed and continuously sublimating wherever solar energy reaches it. The hollow system, viewed this way, is not a curiosity of Mercury's present-day geology. It is a measurement of Mercury's long-term volatile budget, of how much the planet retained from its formation or acquired from subsequent impacts, and how rapidly those reserves are being drawn down. It is the planet's metabolism. Written in bright depressions, the fifth secret moves from the surface to the planet as a whole, and to what the gravity of 4.5 billion years of cooling has recorded in Mercury's longest cliffs. The hollows do not appear everywhere on Mercury's surface. They appear in specific locations, and those locations share a common feature. They occur wherever a globally distributed dark material has been excavated by impact and brought to the surface. Messenger's cameras and spectral instruments identified this material early in the mission and named it low reflectance material, or LRM. It is darker than the average Mercury surface, with a spectral character consistent with carbon-rich compounds. Specifically, graphite. It is found across the planet, embedded in the ejecta of large impact basins, exposed in crater walls where deeper material has been brought to the surface. Wherever LRM is exposed in abundance, hollows tend to follow. The connection led researchers to a specific hypothesis about Mercury's earliest history. During the first 100 million years after formation, Mercury's interior was largely molten, a magma ocean covering the entire planet. As the ocean cooled, minerals crystallized and separated by density. Iron settled toward the center, beginning core formation. Silicates formed the mantle. Graphite, being less dense than silicate melt, would have floated to the top, forming a thin, dark, carbon-rich, primitive crust above the cooling silicate material. This graphite flotation crust hypothesis was proposed before MESSENGER and considered speculative. The discovery of globally distributed LRM with a graphite-consistent spectral signature elevated it into a leading model. Mercury's original surface, the first solid rock the planet ever had, may have been a thin graphite layer, since buried by volcanic eruptions and impact gardening, but persisting in places where large impacts later excavated it from depth. The primitive crust is still there. It has been moved, mixed, and buried, but not destroyed. If this is correct, the hollows are not forming in random, volatile-bearing rock. They are forming in the remnants of Mercury's original surface. The bright depressions that puzzled MESSENGER scientists in 2011 are the places where Mercury is actively losing its oldest layer, the graphite crust that formed when the planet's magma ocean first solidified, somewhere between 4 and 4.5 billion years ago. The solar system's newest geological feature and the solar system's oldest surface material are, in this reading of the data, the same thing. The volatile compounds responsible for the hollows, whatever specifically sublimates into the vacuum and leaves the bright lag deposits, would be the volatile fraction incorporated into the graphite crust during formation, or delivered later by impactors and mixed into the shallow subsurface. Identifying those compounds specifically is one of Bepi Colombo's stated objectives. The improved spatial resolution and sensitivity of its spectrometers will attempt to distinguish between the candidate volatile minerals, chlorides, sulfides, graphite itself, or some combination. Until those measurements are made, the specific chemistry of hollow formation remains one of the most precisely located and least understood geological processes in the solar system. The hollows record what Mercury is losing now. The cliffs record what Mercury has lost over billions of years. They are different measurements of the same slow exhaustion. A planet giving up its heat, its volatiles, and its original surface, one geological age at a time. The fifth secret: the planet that is shrinking. When Mariner 10 made its first close pass of Mercury in March 1974, its cameras returned images of a surface that looked, at first glance, like the Moon, densely cratered, ancient, grey. The resemblance was superficial. Among the features that distinguished Mercury's terrain from the Moon's was a class of large, curving cliffs that had no lunar counterpart. Long, gently curved escarpments crossing multiple craters and topographic features without regard to the underlying terrain structure. One of the largest, which the mission team named Discovery Rupes after James Cook's ship of exploration, extended roughly 550 kilometers across Mercury's southern hemisphere and rose to a height of roughly 1.5 kilometers at its tallest point. Discovery Rupes is a lobate scarp, the surface expression of a thrust fault, a plane along which one block of crust was pushed horizontally over an adjacent block as the underlying planet contracted. The geometry of the faulting compresses the surface. The total horizontal shortening across Discovery Rupes alone amounts to a few kilometers. Multiply this across all the scarps on Mercury's surface, and the sum records how much the planet's crust has shortened as the interior cooled and shrank. Rocky bodies do not expand when they solidify from a melt, they contract. As Mercury's molten interior began to cool and the core and mantle crystallized over billions of years, the planet's volume decreased. The crust above could not expand to accommodate the reduced volume, so it buckled along fault planes, creating the lobate scarps as a planetary record of accumulated compression. From the scarp morphology, you can read the interior history. The size and number of scarps tells you how much the interior cooled. Where the scarps cross craters, you can establish relative timing. The scarp formed after the crater, and if the crater's age can be estimated from its degradation state and the crater density on surrounding terrain, the scarp's age can be bracketed. Mariner 10 covered 45% of Mercury's surface and found some of the largest scarps. Messenger covered all of it. Tom Waters, a planetary geologist at the Smithsonian Institution's Center for Earth and Planetary Studies, led the Messenger tectonic analysis. When the complete global tectonic map was assembled from 4 years of Messenger orbital coverage, it contained roughly 5,900 individual tectonic landforms, lobate scarps, high-relief ridges, and wrinkle ridges. The features appeared at all latitudes, in all terrain types, from ancient heavily cratered highlands to younger smooth volcanic plains laid down over the older terrain in the last 2 billion years. The spatial density of the scarps was higher than the Mariner 10 partial map had suggested. The total extent of Mercury's contractional deformation was larger than the pre-Messenger estimates. The radial contraction, the decrease in Mercury's radius since formation, was revised upward from the roughly 2 kilometers suggested by Mariner 10 data to a range of 5 to 8 kilometers based on the cumulative shortening across all mapped scarps. This corresponds to a decrease in Mercury's diameter of 10 to 16 kilometers. For a planet with a radius of 2,400 kilometers, a 10 to 16 kilometer diameter decrease represents a fractional change of about 1/3 of 1%. This is geologically enormous. To thermally contract by this amount, Mercury's iron-rich interior must have lost a substantial fraction of its formation heat over 4.5 billion years. But the revised estimate introduced a discrepancy that the thermal models had not predicted. Thermal models of Mercury's evolution, simulations of how the planet cooled from a mostly or fully molten starting state to its current condition, had predicted a radial contraction of 10 to 20 kilometers. The Messenger measurement of 5 to 8 kilometers of radial contraction is less than half the lower end of those predictions. The planet shrank less than it should have. In planetary geology, this kind of discrepancy is not a rounding error. It means something fundamental about the thermal model is wrong. 2 interpretations are possible, and researchers have not reached consensus on which is correct. The first, the thermal models overestimate how efficiently Mercury loses heat. If Mercury's mantle has lower thermal conductivity than the models assume, or if its composition retains heat differently, the interior would cool more slowly. Less total cooling over 4.5 billion years means less total contraction. The planet has not yet finished cooling, and the 5 to 8 kilometer measurement is where the cooling stands today, with more contraction still ahead. The second, Mercury has additional heat sources the models do not include. Tidal heating from the Sun's gravitational pull on Mercury's eccentric orbit may contribute. Radiogenic heating from a mantle richer in radioactive elements than assumed may contribute. Either would keep the interior warmer longer, slowing the contraction rate. What tips the analysis toward ongoing activity rather than simply a slower than expected cooling history is the morphology of the youngest scarps. Paul Byrne at Washington University in St. Louis and colleagues published in Nature Geoscience in 2014 an analysis of Mercury's youngest tectonic features, scarps whose morphology is so fresh and undegraded, with crisp edges and sharp wall profiles, that they cannot have been sitting on the surface for billions of years of micrometeorite bombardment and thermal cycling without showing more degradation. Some of these young scarps cut through relatively fresh impact craters, meaning the craters formed first and the faults developed afterward. Age estimates for the surrounding terrain, based on crater density, suggest some of these features formed within the last 50 to 300 million years. Mercury may still be tectonically active. For a planet 1/18th Earth's mass, this was not expected. Earth is active because of its large size and the ongoing convection in its mantle. Mercury was supposed to have finished its geological active phase long ago. The combination of the liquid outer core, the contraction less than thermal models predicted, and the young fault morphology all point toward an interior that is still doing something. Lobate scarps preserve the amount of contraction at a surface location. They do not record the rate at which that contraction occurred. A scarp that formed slowly over 1 billion years and a scarp that formed rapidly in a geologically brief episode are morphologically identical after the same duration of subsequent surface processes. The accumulated shortening is in the topography. The timing is not. Distinguishing slow, ongoing contraction from a past episode of rapid cooling requires seismological data, measurements of the deep interior using waves from Mercury quakes. The same technique that allowed Earth's internal structure to be mapped in detail, beginning in the late 19th century. Mercury has never been instrumented seismically. No mission to Mercury has placed a seismometer on its surface. The subsurface structure, the inner core radius, the depth of major phase boundaries, all of these are inferred from gravitational and magnetic measurements made from orbit, at distances of hundreds to thousands of kilometers from the features they constrain. Bepi Colombo carries improved gravity mapping instruments compared to Messenger. Its refined gravity maps will tighten the constraints on Mercury's interior density structure and narrow the range of acceptable interior models. But they will not resolve the seismological ambiguity. A seismometer on Mercury's surface would take years to accumulate meaningful data, and operating a sensitive geophysical instrument on a surface that swings from 430 degrees Celsius during the day to negative 180 degrees at night is an engineering problem that no planetary mission has solved. The scarps, the liquid core, the magnetic field offset, the volatile surface, the hollows, all of them are inferences from remote sensing, confident inferences built on multiple independent measurements, but not direct contact with the interior. The deep structure of Mercury has been probed from the outside. It has not been opened. The strongest evidence that Mercury is still tectonically active comes not from a single dramatic discovery, but from the careful reading of landform shapes, an interpretive technique as old as geology itself, applied to a planet where no geologist has ever stood. Paul Byrne, who led the 2014 analysis of Mercury's youngest tectonic features, described the diagnostic criteria in terms that geologists use for any planetary surface. A fresh thrust fault scarp has crisp angular wall profiles with steep slopes close to the angle of repose for Mercury's surface material. Secondary craters from boulder falls are visible at the base of fresh scarps. The scarp crest is sharp, not rounded. The surface immediately adjacent to the scarp shows compression features, small ridges and buckled terrain that have not been smoothed by subsequent impact gardening. Over time, all of these features degrade. The walls slump under the influence of seismic shaking from ongoing impacts. The secondary craters fill in, the crest rounds, the compression features flatten. A scarp that has sat undisturbed for 1 billion years in Mercury's slowly but continuously bombarded environment is noticeably more degraded than one formed recently. The young scarps Byrne's team identified have the morphological freshness of features that have not experienced extensive post-formation degradation. They could not have been sitting on Mercury's surface for billions of years and still look the way they do. The estimate of 50 to 300 million years for the youngest features is a range, not a precise number, reflecting the uncertainty in the crater production rate models and in the specific degradation rate for Mercury's surface material, but the direction of the constraint is unambiguous. These scarps are young, and young means the interior is still producing thrust fault activity. The craters that young scarps cut through provide the relative timing constraint. If a scarp cuts across a crater, the crater is older than the scarp. It was there when the fault formed and was deformed by the faulting event. Estimating the age of that crater from the crater production rate at Mercury's orbital location gives an absolute age constraint on the fault. The craters cut by Mercury's youngest scarps have age estimates consistent with the same few 100 million-year window derived from the morphological freshness analysis. Two independent lines of evidence, both pointing to the same age range. What this means for the thermal evolution picture is specific. If Mercury were simply a planet that had cooled rapidly and was now geologically dormant, waiting passively for the sun to expand and engulf it, the scarps would all be ancient, all equally degraded, recording a compressional history that ended long ago. The young scarps show that compressional deformation is ongoing. The interior is still cooling, the stress in the crust is still building. The surface is still responding. This is the part of Mercury's story that most surprises planetary scientists who come to it from experience with other small rocky bodies. The Moon is geologically dormant. Its last major volcanic activity ceased roughly 3 billion years ago, and its tectonic activity, if it occurs at all, is so low level as to be debated. The large asteroids are geologically inactive. Even Mars, with its towering volcanoes and ancient river valleys, shows no definitive evidence of active geological processes at the present day. Mercury, smaller than any of them except the Moon, appears to be the most geologically alive of all the small rocky bodies in the solar system. The reason is probably the large core. A body that is mostly iron, with only a thin rocky shell, retains heat differently from a body with a large silicate mantle. The iron core loses heat slowly through the relatively insulating silicate layer above it. The specific heat content of a large liquid iron outer core is enormous. The thermal reservoir, represented by 2,000 kilometers of slowly cooling liquid metal, dwarfs what a similarly sized body with a smaller core would carry. Mercury's interior may simply have more heat to lose, and more time remaining in which to lose it, than a planet its size would seem to have. The sixth secret is about the spacecraft that got closer than any instrument before it, and about what it found in its final weeks of operation, and what it could not find in 4 years. The scarps record Mercury's geological present, the slow compression of a cooling planet. They say nothing about the geological past Mercury went through before the compression dominated. That past was volcanic. Messenger's imaging found extensive smooth plains covering roughly 40% of Mercury's surface. Much of this material is volcanic, lava flows that flooded older cratered terrain, burying it beneath sheets of solidified magma. The largest single volcanic province is the Northern Volcanic Plains, a continuous region of volcanic rock covering roughly 7% of Mercury's total surface area, centered on the North Polar region and extending southward into mid-latitudes. Crater counting on this terrain, estimating its age from the density of small impact craters that have accumulated since it was emplaced, places the age of the Northern Volcanic Plains at roughly 3.5 billion years. Mercury was, in its geological middle age, an actively volcanic planet. Messenger also found evidence of explosive volcanism. Pyroclastic deposits surrounding ancient volcanic vents created by eruptions in which gas-rich magma fragmented explosively rather than flowing quietly. These deposits are the surface evidence of volatiles in Mercury's mantle, a magma that contains dissolved gases. When depressurized as it rises to the surface, can explode rather than flow. Explosive volcanism on Mercury was not expected from pre-Messenger models, because those models predicted a volatile, poor interior. The pyroclastic deposits are direct evidence that Mercury's deep interior retained significant volatile content at the time of these eruptions. Several billion years ago, the timeline emerging from Messenger's volcanic record shows a sequence. Early Mercury, in the first billion years, widespread volcanic activity, flooding ancient terrain with lavas, and occasionally erupting explosively from volatile rich magmas. Middle Mercury, from roughly 3.5 to 2 billion years ago, volcanic activity declining, with the last major eruptions emplacing the smooth plains. Late Mercury, from roughly 2 billion years to the present, volcanism effectively ceased, replaced by compressional tectonics as the contracting interior buckled the crust into scarps. Present Mercury. No active volcanism, but young scarps suggest tectonic activity continues, and the hollows show that volatile loss from the shallow subsurface is ongoing. The interesting overlap is at the transition. Some of the youngest lobate scarps cut through volcanic terrain, meaning the contractional phase had already begun, while volcanism was still ongoing. Some of the young volcanic features are themselves slightly deformed by faults, meaning they were emplaced into a crust already under compressional stress. The two processes, volcanic activity and tectonic compression, were occurring simultaneously for a period, probably between 3 and 2 billion years ago, as Mercury's interior crossed the temperature threshold below which volcanism became impossible, while contractional cooling continued. This overlap was not predicted by simple thermal models that treated Mercury as a uniformly cooling sphere. It requires a more structured interior, possibly a compositionally stratified mantle that lost heat unevenly, or a thicker than expected volcanic crust that insulated the deeper interior. Both possibilities are consistent with Mercury's anomalous composition. Neither has been confirmed. Mercury's geological history, read from its surface, is a record of progressive loss. First the magma ocean, then the volcanic activity, then the atmospheric gases, and now the volatile subsurface through the hollows. The planet has been releasing its formation, energy, and materials into space since it first solidified. The scarps mark where it shrank. The hollow, bright floors mark where it is still losing itself. Quietly, crater by crater, under a sky it cannot feel. The sixth secret, the question the spacecraft died answering. Messenger launched in August 2004. It spent 6 years and 8 months in transit, making 1 flyby of Earth, 2 of Venus, and 3 of Mercury before finally breaking into Mercury orbit in March 2011. Its nominal mission was 1 Earth year. It was extended once, then again. By early 2015, it had been in orbit for nearly 4 years, completed more than 4,000 orbits, and transmitted more than 270,000 images. Spacecraft in orbit around Mercury require regular thruster firings to counteract the gravitational perturbations from the Sun and other planets, which would otherwise slowly decay the orbit until impact. Messenger's mission controllers at the Johns Hopkins University Applied Physics Laboratory had stretched the mission as long as possible, using helium pressurant gas from emptied fuel tanks as a last source of thrust after the main propellant was exhausted. By April 2015, the helium-2 was nearly depleted. The decision was straightforward. Rather than allow an uncontrolled impact, the team would use the remaining helium for planned orbit adjustments that allowed the orbit to decay in a controlled way, dipping as low as possible before the end. The strategy extracted maximum scientific return from the final weeks. In the last months of orbital operations, Messenger's closest approach point descended from its normal altitude of hundreds of kilometers to altitudes below 20 kilometers. And in some passes, below 5 kilometers above Mercury's surface. A spacecraft weighing, at that point, only the mass of its structure and instruments. Fuel long spent, skimming over terrain at roughly 14,000 kilometers per hour. At 5 kilometers altitude, Mercury's surface fills most of the camera field of view. The images from these final passes have spatial resolutions below 1 meter per pixel in some cases, detail that had never been possible from orbital distance and has not been surpassed since. The images returned in Messenger's final weeks of operation changed the measurement precision of every feature they depicted. Individual hollows visible in complete isolation, young fault scarps with their wall profiles resolved to individual boulders, polar crater floors with their dark organic caps, and exposed ice patches mapped in detail that the earlier, higher altitude coverage could not provide. Scientists who had been interpreting Messenger data for 4 years found that the final phase data required revisions to the quantitative estimates they had published from the higher altitude images. On the 30th of April 2015, Messenger impacted Mercury's surface near the North Pole. The spacecraft had a mass, at the end of its operational life, of approximately 500 kilograms. Most of its original mass had been propellant, used across 6 years of transit and 4 years of orbital maintenance. What struck the surface was a structure of aluminum, titanium, steel, and electronics. The impact created a crater estimated at 16 meters in diameter. 16 meters. On a planet covered with craters ranging from a few meters to hundreds of kilometers. Messenger's final resting place is one of the smallest impact features on Mercury's surface. Smaller than the hollows it spent 4 years imaging, smaller than the volcanic vents it found in the ancient terrain, smaller than the resolution limit of every image it sent home. The crater is not visible in Messenger's own data. The impact site has been estimated from the final orbital geometry, and it was searched for in subsequent observations and radar measurements from Earth. It is there, a 16-meter mark in the ancient terrain near the North Pole, the most precisely dated impact crater on Mercury, created by the one human artifact that has touched Mercury's surface. The mission operations team at the Applied Physics Laboratory had been running Messenger for 10 years and 8 months. Longer than any member of the initial team had expected when the spacecraft launched. When contact was lost, immediately after the impact, the acknowledgement from the team was what you would expect from a group of engineers who had prepared for this moment for months and still found it abrupt, professional, and quiet. The data Messenger collected continued to generate publications for years afterward. New papers from Messenger observations appeared in 2016, 2017, 2018, and beyond, refining the polar ice depth estimates, extending the tectonic map, characterizing the hollow distribution in full global context. The instrument was gone. The information it had gathered was not. The central question it had been sent to answer, why is Mercury made of what it is made of, remained open. On the 20th of October 2018, an Ariane 5 rocket launched from the Guiana Space Center in Kourou and placed in orbit a spacecraft stack consisting of 2 separate planetary orbiters. The Mercury Planetary Orbiter, built by the European Space Agency, and the Mercury Magnetospheric Orbiter, built by the Japan Aerospace Exploration Agency. The mission is Bepi Colombo, named for Giuseppe Colombo, the Italian mathematician who first recognized Mercury's 3-2 spin-orbit resonance in the 1,960 seconds, and designed the gravity assist trajectory that made Mariner 10's Mercury flybys possible. Colombo had died in 1984. The mission named for him was still 2 decades from reaching its target. Bepi Colombo spent 6 years in transit, using the gravity of Earth, Venus, and Mercury itself. 6 Mercury flybys, to slow down enough to be captured by Mercury's gravity in late 2025. The 2 spacecraft architecture is its primary technical advantage over Messenger. The planetary orbiter will map the surface, magnetic field, exosphere, and gravity from a relatively low orbit, while the magnetospheric orbiter flies higher and measures the magnetic field structure and solar wind interaction simultaneously. Messenger had only a single vantage point. Bepi Colombo has 2. The instrument complement is more extensive than Messenger's and, in several areas, more sensitive. The gamma-ray and neutron spectrometer suite will map Mercury's surface elemental composition with higher spatial resolution, potentially identifying the specific volatile compounds associated with the hollows. The magnetometer system, measuring the field from 2 positions simultaneously, will produce a 3-dimensional model of Mercury's dynamo geometry that a single spacecraft measurement could never provide. The radio science experiment will refine the gravity field measurements, constraining the interior density structure at smaller scales than Messenger achieved. Bepi Colombo will not land on Mercury. It will not place a seismometer. It will not return a sample. the thermal environment on Mercury's surface. 430 degrees Celsius in daylight, negative 180 at night, with a daily cycling period of 59 Earth days, exceeds the operational limits of any surface probe currently under development. A Mercury lander would require a thermal management system unlike anything in the current inventory of planetary engineering, and no such mission is in any space agency's current plan. After Mariner 10, Messenger, Bepi Colombo, and more than 50 years of study since the first close flyby, the central question of Mercury has not been answered. The planet closest to the Sun has a core occupying more than 80% of its radius, and no planetary formation model fully explains how this happened. Its magnetic field is geometrically unlike any other known dynamo, displaced northward by 20% of the planet's radius, and the deep interior conditions that produce this geometry cannot be measured from orbit. Its polar craters contain water ice under a dark organic cap, preserved since before complex life appeared on Earth, delivered by comets whose trajectory may have also seeded the oceans of an early Earth. Its surface is actively losing volatile material through a sublimation mechanism whose specific chemistry has not been identified and whose energy source is not established. Its ancient terrain records a contraction history inconsistent with thermal models, and its youngest faults suggest the planet may still be geologically active. Every one of these findings contradicts the assumption that Mercury would be the simplest rocky body to understand. Before Messenger, the conventional picture was of a small, dead, geologically uncomplicated rock. The inner solar system's afterthought, too close to the Sun to have retained much of interest, too small to have maintained geological activity. Models of rocky planet formation were calibrated primarily on Earth, Mars, Venus, and the Moon. Mercury was expected to fit. The planet closest to the Sun turned out to be the one farthest from understood. What Messenger demonstrated, and what Bepi Colombo is continuing to characterize, is not merely a list of unexpected discoveries. It is a systematic demonstration that the framework used to explain how the inner solar system assembled does not account for the body closest to the star. If the model fails there, at its simplest case, its most accessible test. The question is not only what Mercury is, it is what the model was missing that produced so many incorrect predictions, and how many of the assumed simplicities of the other rocky planets are masking the same kind of patient contradiction, waiting for a spacecraft close enough to resolve them. Mercury has had 4.5 billion years to keep its secrets. It has been patient. The instruments humanity has sent so far have found 6 of those secrets. The interior, the sealed iron core 400 kilometers below the surface, the liquid outer core whose sulfur content we infer but have not measured, the inner core boundary whose position we estimate but have not located, the seismic structure that no instrument has ever touched, remains closed. Not forever, only for now. The questions have boundaries. The answers are inside the planet. Eventually, something will reach them. The formation question, why Mercury has the core it has, is not unresolvable in principle. It requires data that does not yet exist, from instruments that have not yet landed on a surface that no mission is currently funded to reach. The specific data needed is known, and knowing exactly what you need to know and exactly how to get it is not the same as not knowing the answer. It is a different kind of not knowing, bounded, specific, addressable. Seismology is the most powerful tool available for probing planetary interiors. On Earth, the global seismic network established in the 20th century mapped the internal structure with a precision that no other remote measurement could approach. The radius of the liquid outer core, the boundary of the solid inner core, the depth of the major mantle phase transitions, the thickness and composition of the crust at any point on the planet. A year of seismic data from a single station on Mercury's surface would constrain the inner core radius to a precision that would discriminate between the giant impact hypothesis and the high temperature condensation hypothesis, because each predicts a different inner core size and core mantle boundary composition. Sample return is the other critical data source. A gram of rock from Mercury's mantle, from a depth below the volcanic overprinting, from material that preserves the original formation composition, would allow geochemists to measure the age of last melting, the pressure and temperature of crystallization, and the trace element ratios that uniquely fingerprint the formation environment. No isotope ratio, no trace element concentration, no spectral measurement from orbit would be needed. The rock itself would carry the answer. Both of these require landing on Mercury and surviving long enough to make measurements. The thermal environment, the same extreme temperature swing that makes Mercury's polar ice remarkable, from 430 degrees during the day to negative 180 at night, makes this an engineering problem of the first order. A lander capable of surviving Mercury's surface environment would require thermal management systems unlike anything currently operational and a power system able to function in the extreme radiation environment near the Sunday. None of the currently planned missions will attempt this. Bepi Colombo's data will be transmitted and analysed through the late 2020 seconds and into the 2030 seconds. Its improved measurements will tighten the constraints on every open question: the interior density structure, the field geometry, the surface composition, the polar deposit chemistry. None of these will close the formation question directly, but they will narrow the parameter space enough that, combined with improved planetary formation models, the answer may become narrowed to a choice between two specific scenarios rather than an open field of possibilities. That is meaningful scientific progress, even if it is not resolution. What Mercury offers, beyond the specific answers to its specific questions, is a demonstration of the limits of scale-based reasoning in planetary science. The assumption that a small, close, geologically simple planet would be the easiest to understand was a form of intuition built on familiarity with Earth and the larger planets. Mercury failed that intuition systematically across every measurement that was made. The interior was wrong, the surface was wrong, the field was wrong, the poles were wrong, the geological activity was wrong. The planet closest to the Sun turned out to be the one farthest from any prior expectation, not because it is exotic. Its physics is ordinary. Its composition is made of the same elements as every other rocky body. But because the combination, the specific proportions, and the specific history is unique enough that no model built primarily on other planets' data could predict it, the questions Mercury raises about its own formation may be questions about the formation of the inner solar system. If the standard model produces the wrong answer for the simplest rocky body at the innermost orbit, the same model was used to describe how Earth, Venus, and Mars assembled. How much of what we think we know about those planets is wrong in the same way Mercury was wrong? Not obviously, not dramatically, but quietly, in the interior. Waiting for the right instrument to arrive, Mercury does not have an answer to this. It has been patient for 4.5 billion years. It can wait a little longer. What it has already given is not nothing. The 6 anomalies described here, the impossible core, the offset field, the polar ice, the hollows, the undercontraction, and the unanswered formation question, are not 6 unrelated puzzles. They are 6 angles on the same underlying fact. Mercury was built differently, and the model used to describe how the inner solar system assembled did not anticipate it. The significance of that failure depends on what you think the model is for. If it is an approximation for understanding the broad strokes of planetary formation, the failure is local. Mercury is an anomaly. The other planets are fine. If the model is meant to describe the physical process in enough detail that you can trust its predictions for any individual body, the failure is more serious. Mercury is not a statistical outlier in the way that exceptional cases are sometimes dismissed. It is the closest test case, the simplest body by conventional metrics, and the one that failed the prediction most thoroughly. The planet closest to the Sun is also the one that, 4.5 billion years later, has kept the most of its formation history intact. In a thick iron core, in volatile rich rocks, in a barely there atmosphere exhaled from those rocks, in frozen water at its poles, and in a slowly cooling interior that is still, quietly, reshaping the surface. It is not a dead world, it is a patient one. And patient things, given enough time, eventually give up what they are holding. The universe will still be here when you wake up. So will we. Good night. The universe will still be here when you wake up. So will we. Good night.